Okay, welcome back everybody for Stephen's last lecture. So with nothing more to be said, please, Stephen. And thank you, those of you online attending. Thank you for coming back. And thank you, Stephen.
Thanks very much. So we've gone slightly late a couple times now. I'm going to definitely not fill the whole hour here, but I want to try to finish with some open problem or two, since we've covered a lot of like somewhat classical things. But first, to remind you, this is what we just finished proving. And then to get back to like right-angled Artin groups and right-angled Coxeter groups, let's see some examples. So basically, we've proven that polyhedral products over flag complexes anyway allow us to get nice polyhedral product models of classifying spaces. So what sort of groups do we get? Corollary G1 to GM are some discrete groups, right? So, okay, first let me mention these things were aspherical, right? Classifying spaces, if and only if K is flag. And we had this fibration with this as the total space and a different polyhedral product, EG, comma G, as the fiber. So notice those would also be aspherical by the long exact sequence, that fibration. So first corollary is that this guy we can say is also aspherical if and only if K is flag. Okay, so just those two examples give us lots of interesting classifying spaces, I think. So this is because of the fibration we've seen a few times. Kumar was just asking about. So what are they classifying spaces of? Well, when you take pi1, this map is inducing like an abelianization map. So corollary and pi1 of this aspherical space really looks like the kernel of this induced map, right? So pi1 of this we just showed is the graph product, G to the gamma. Pi1 of this is just a product of G's. And at least when I guess at least when these groups themselves, like the individual GIs are abelian, it's like the abelianization, like sort of coordinate-wise abelianization map, right? So this kernel is just going to be a coordinate subgroup, as you might guess if you looked at that long exact sequence. Or sorry, I should say commutator subgroup. Okay, so examples. We have these right-angled Artin groups. Let K be flag for the rest of the talk with one skeleton graph that we'll call gamma. Then, okay, I'll write some BG comma point examples in this column and some EG comma G examples in this column. So when G was the integers, we said that corresponded to graph products just being rags, right-angled Artin groups. So like this polyhedral product, PG comma star, B of an Artin group, and this is just B of the commutator, classifying space of like commutator subgroup of an Artin group. A gamma. Right, here's my EZ comma Z. And the other interesting case was Z mod 2. So here the polyhedral product was just like the real moment angle complex, which we had some notation for in previous lectures, but recall that was just defined to be the polyhedral product like RP infinity comma a point, right, which is exactly B of Z2. So that one is classifying space of this right-angled Coxeter group. And same thing over here, classifying space of the commutator subgroup. Pardon me, this should have been the Davis-Januszkiewicz space. Our DJ was our notation, and then over here, the fiber, that was where the real moment angle complex was. So R K. Over here is polyhedral product D1 comma S naught. Like EZ mod 2 comma Z mod 2. So that's B of this commutator. So these are groups that come up a lot in geometric group theory, low dimensional topology. And now you can see why the Hoxter formula that we reviewed at the beginning could be used to compute the cohomology of these groups and lots of others like it, right? Take your favorite ingredient discrete groups G to produce lots of other examples, put all those under the heading of polyhedral product models of classifying spaces. But then you can do some more also. So in the first day, when we were just going over like polyhedral products as they arise in toric topology, moment angle complexes were interesting spaces and the Davis-Januszkiewicz spaces, but there were lots of other spaces that weren't quite polyhedral products, like toric manifolds. And we said that the map from moment angle complex to Davis-Januszkiewicz space factors through every toric space or every toric manifold, and lots of other spaces that aren't necessarily manifold, right? You can get all kinds of like partial quotients of a moment angle complex. There's quotienting out by a subtorus or discrete subgroups of the big torus acting on these things. So any sort of space like that that you can fit in between these two things, you can check is also going to be aspherical when K is flag. You can compute what the fundamental group is. And as you might suspect, geometric group theorists do a lot with like subgroups of right-angled Coxeter groups and right-angled Artin groups. And that's exactly what these groups in between are going to look like. So I just wanted to mention one example. I'll just say can also get classifying spaces like not as polyhedral products, but as quotients of polyhedral products. Right, which included all kinds of toric spaces, at least when the group we took was like S1 or Z mod 2, right? That would correspond to like real toric manifolds or small covers as they're called as well. So one interesting group, family of groups called Desvina-Brady groups. These are just like Artin and Coxeter groups, right-angled anyway. Just a nice family of groups associated to any graph, usually written E sub gamma, and they're defined to just be the kernel, the map from this right-angled Artin group here to Z, the like ingredient group that gave rise to it as a graph product. By the group homomorphism that just sends each of these GIs, right? Remember we had a group presentation for Carleton group, just M generators, one for each vertex of your graph, and that was it, right? Aside from these commutator relations for edges. Right-angled Coxeter, it's the exact same thing, except all of our generators also squared to the identity. So yeah, Best-Wiener-Brady groups are really talked about in all of these contexts, right? You could put a right-angled Coxeter group here, or take any discrete group, you might get what you call generalized Best-Wiener-Brady groups. So let me just go through the case, since we actually talked about toric space or quotients of moment angle complexes, but not more general polyhedral products that look weird like this. So let me, instead of using this one, go through an example where we define the Best-Wiener-Brady group as a subgroup of a right-angled Coxeter group. But exactly the same construction. So my right-angled Coxeter group, take the exact same group homomorphism, sending every single generator to a generator over here. So these are some sort of famous groups. Best-Wiener and Brady introduced them and used them to prove that one of two very famous conjectures is false. The Eilenberg-Genea conjecture or the Whitehead conjecture. Both of these deal with aspherical spaces of dimension 2. I think Eilenberg-Genea is the one that says the cohomological dimension of a group should equal its geometric dimension. So this is known in all higher dimensions. The conjecture is really about dimension 2. Is it true that if a group has a cohomological dimension 2, that it admits a classifying space of topological dimension 2? And then the Whitehead conjecture, saying something like subcomplexes of two-dimensional aspherical spaces are aspherical. So these are two open conjectures, and Best-Wiener and Brady used groups like these to show somehow that one of those two conjectures is false, and I think it's still open which of the two conjectures fails. Okay, so let's try to get a classifying space B of B gamma by thinking of quotients of like this space. So you might remember from the first lecture, a picture, a diagram I drew like this. So I'll start with my real moment angle complex and the sort of fundamental vibration that it sits in, mapping to Davis-Januszkiewicz. Without the R's here, the fiber was just a torus. Now to be like a 2 torus, right? This elementary abelian 2 group, Z mod 2 to the M. And the idea of toric manifolds or quasi-toric manifolds was that if you could find a subtorus up here, such that when you restrict this action, it's free, then you take the quotient, and that's called a toric manifold. And more generally, even if it doesn't act freely, we would just take the homotopy quotient, and we similarly get maps down here, right? So take any, let's just think of a subtorus, like M minus N sitting in here, and let's just quotient out by that first. Restrict this action and quotient, get some space that I'll call M. So I'm thinking of it as sort of analogous to a toric manifold. Have some residual like Z mod 2 to the N, just going to act on that with homotopy quotient, Davis-Januszkiewicz space. Okay, so now let's specialize to the case where K is flag, call gamma its one skeleton. Then we know everything in sight is a classifying space, or this square anyway are all classifying spaces. We know of what groups in these positions. So pi 1 of this diagram is going to give you right here classifying space of the right-angled Coxeter group or its commutator subgroup.
You need to put the K on the place.
You're right. Thank you. Thanks. So we want to arrange to have pi1 of this, right? We're trying to get some quotient of a moment angle complex as the classifying space of Besvina-Brady. So I would like to put B gamma, that group here. So this commutator subgroup in fundamental groups is just mapping to right-angled Coxeter group. So to pick right M, I would have this fundamental group. I already know just from the long exact sequences of these fibrations that this is like an aspherical space. Just want to arrange to have the right fundamental group. How do you do that? Well, you have to like pick the right subtorus that's giving you the right space. But notice that to do that, if we're just thinking of the definition of the Besvina-Brady group, we could think of this whole diagram. Now, this is a principal fibration classified by a map into B of this. Right, so down here we have like B of Z mod 2 to the M. And this is a group homomorphism, right? If this is a subtorus, a subgroup, this is the quotient. So I can hit B, that map, to get over to B of Z mod 2 to the N. Over here, this is sort of like an abelianization map, right? Fundamental group of this is just Z mod 2 to the M, Z mod 2 to the N. So now you might see what we have to do, right? We also want to specialize to the case N equals 1. Since Besvina-Brady is defined as the kernel of a map like this into just Z mod 2 to the 1, right? So take N equals 1. And let's just think of choosing this map correctly to put Besvina-Brady in the right spot. Yeah, so if that's F and we're taking pi 1, this is like the induced map on fundamental groups, F star. So just choose F star to be that group homomorphism.
N equals 1 on the right as well? No.
Yeah, thank you. Let's put a 1 there. Is that what you meant? Yeah, let's choose this homomorphism. And then F will just be B of that group homomorphism, right? And then we'll take a homotopy fiber instead of a kernel over here. So take F star to be this map, whatever I said, Z mod 2 to the M to Z mod 2 to the 1. So we like precompose with this abelianization map followed by F star. And then take this map to just be defined by the quotient. Fill in the rest of these diagrams by taking kernels here, and taking fibers back here. So all of my generators of GI are going to 1 here, right? That's the obvious group homomorphism. This will be an M-1 torus.
Steve?
Yes.
Just a quick question. So in your diagram, in your diagram on the right, your top left thing, is it like?
That's a shame.
No, I can see the diagram. I have a question about the thing.
Oh, you can see it. Sorry. Yeah. Okay.
Yeah. So on the top left thing, like the B of commutator, is that commutator in the subscript, or is it like we should?
So where am I missing a B?
No, you're like the B of this commutator W gamma, right? That commutator W gamma, is it in the subscript?
Oh, this B.
Yeah.
Thank you very much. Yeah, when we specialized to K being flagged, this was B of that. Thank you. Was that the gist of it?
Oh, thanks.
Thank you very much. Okay, so this might give you some idea of how you could construct lots of classifying spaces as generalizations of like toric spaces. And there's a big analogy between, we could then take like G equals S1, right? And think of the ordinary Davis-Januszkiewicz space and the ordinary moment angle complexes. We saw that those are simply connected, so they don't fit into this picture. And S1 is not discrete. That's another reason it doesn't fit into this picture. But there's this analogy between the topology of moment angle complexes, and especially their Pontryagin rings, so the homology of their loop spaces. That's what behaves like the fundamental groups of these real analogs. So there's a bunch of theorems that I won't write down that say things like pi1 of this space is free if and only if, a free group if and only if the Pontryagin ring of the ordinary ZK, the loop space homology, of ZK is free as like an associative algebra. Sorry, that really should have been about this and its complex analog. And same thing for the moment angle complexes. Loop space homology will look like a one-relator algebra, associative algebra, so the next best thing to a free associative algebra, if and only if pi1 of this thing is a one-relator group. So there's this big analogy, and sometimes there are nice presentations for the loop space homology of a moment angle complex. Well, when K is flag, there's certainly a nice presentation for this space without the R. It's looking very much like presentations of these groups that you get. So there's a whole sequence of theorems on these two sides in group theory and in topology. And it's not just about the Pontryagin rings of moment angle complexes, but also their homotopy type. So like right angle Coxeter group is free if and only if the moment angle complex associated to this flag K is a wedge of spheres. It's a problem we talked about earlier, identifying which moment angle complexes are wedges of spheres or connected sums of sphere products and so on. So there's this beautiful analogy going on, and you could do all of this with G equals S1, right? There's some sort of, let me just say in the complex case, so like G in that picture to be a circle, we get some sort of analogous toric space or quotient of an ordinary moment angle complex, which you might call a Svina-Brady partial quotient. ZK, simply connected space. Let me just keep calling it M, even though it won't necessarily be a manifold, but it's just like going to be the exact same thing as up here, right? ZK modulo instead of a Z mod 2 to the M minus 1, it's like an M minus 1 torus. Right, H here to indicate the homotopy quotient. And what I'm saying in this analogy is that the topology of M, and especially Pontryagin ring, should behave like the Svina-Brady group. Thought of as a subspace either of the Artin group or the right-angled Coxeter group. And there are many, many results on the group theory side about Svina-Brady groups and similar subgroups of these things. In particular, people know when this thing is finitely presented. And when it is, there's a really nice combinatorial presentation for this group that you can read off from your defining graph gamma. And it looks sort of like presentations we see in toric topology for Pontryagin rings sometimes. There are results about when this thing is again a rag, like A of gamma for some different gamma. Weirdly, that happens. Lots of results of various authors about like finiteness properties of things in terms of the the graph or the geometric realization of the simplicial complex here, like the flag complex of gamma. Yeah, and of course, lots of results in the group cohomology, this. And so are there topological analogs of these? Being very vague here. So the problem, I would just say, is like further develop this analogy. Okay, and now I want to sort of finish with a very different problem. Something called the Charney-Davis conjecture, which if you Googled, I don't think would necessarily see anything about polyhedral products or real moment angle complexes, but I want to phrase it in terms of real moment angle complexes and see what we can do with it. Okay, so let me start with like an even more general conjecture, which was originally stated by Hopf and later by Thurston in a more topological context. Weirdly, I think of Hopf being more associated with topology and Thurston with geometry, but this is going to go the opposite way. So if M is an even dimensional manifold, let's say closed non-positively curved is what Hopf was interested in. And then later, Thurston generalized the conjecture to just any aspherical manifold. Okay, so this is more general than that. So just think if M is an even dimensional aspherical manifold, then in the Hopf case, this is called the Hopf conjecture, or one of a few things called the Hopf conjecture. And in the aspherical or Thurston case, it's just usually called the Euler characteristic conjecture. So it's guessing that -1 to the n, right? So half the dimension of our manifold times the Euler characteristic should be non-positive. I guess it's really a conjecture just for all dimensional manifolds, but when M is odd, that's the case where you don't have like an honest middle cohomology group, right? So by Poincare duality, the alternating sum of your Betti numbers is always just 0. But for even dimensional manifolds, there's like a true middle dimensional cohomology group. So an alternating sum of your Betti numbers doesn't just cancel out. And what the Euler characteristic there is very mysterious. It's a very old conjecture and not much is known, but certainly true when n equals 1, right? Here we can say, you've got the classification of surfaces. Telling you the characteristic is a complete invariant. So surface genus G, 2 minus 2g, which is certainly non-positive, as it should be, right, for n equals 1. Okay, now let me specialize before saying what else is known in higher dimensions. I think, you know, there's not that much to say about what else is known in higher dimensions, really. But one setting where flag complexes come up, turn out to give a relation to this very general conjecture, is in a well-known result of Gromov. Okay, let me just write it down in a second. But it's a special case, this conjecture, or discrete analog, which takes as a starting point a result of Gromov that says the following: a like cubical, what do they call it? Cubical complex, I guess, instead of a cell complex. A cubical complex is non-positively curved. So instead of manifolds, we're going to think of discrete objects that geometric group theorists like. So non-positively curved in some like cat zero sense, or you know, Alexandrov sense. Sorry?
Conditional GD6.
Yeah, exactly. The same, yeah. Sort of discrete notion of not about smooth manifolds anymore, but if and only if the link of each vertex in your cubical complex, whatever that is flag. Okay, so the next conjecture I'm going to write down is usually thought of as like a discrete analog of this, not for manifolds, but for cubical complexes with this property, and this is where flag complexes are going to come in. Charney-Davis conjecture. We could phrase as follows. So if K is flag, let's say it's like a flag 2n minus 1 sphere. By that I just mean it's a simplicial complex that triangulates 2n minus 1 sphere. Then same thing, minus 1 to the n, the Euler characteristic of the real moment angle complex should be non-negative. Okay, so this is the one I'm saying if you go Google the Charney-Davis conjecture, I don't think you'll see it phrased this way. Instead, it's thought of as some discrete analog of this, but from our polyhedral product or toric topology point of view, we can also just think of it as literally a special case of this, right? Because flag gives us that this is aspherical, right? So instead of thinking of this analogy of non-positive curvature and Hopf's conjecture, think of Thurston's version, asking about all aspherical manifolds. We just saw that flag gives us asphericity of the real moment angle complex. And being a sphere triangulation, we saw in a previous lecture, tells us that this is actually a manifold. So this is literally a special case of that here. Okay, so flagness gives us one hypothesis over there. and geometric realization of K being a sphere, dimension 2n minus 1, gives that this is a manifold, and it gives us the manifold of the right dimension. Okay, maybe not smooth, I guess, but certainly if it's like a polytopic triangulation of the 2n minus 1 sphere, this would be a smooth manifold, aspherical. This also tells us, that certain fundamental group here was a commutator subgroup, the right angle Coxeter group, right? So this tells us that those commutator subgroups are often like surface groups or three manifold groups, which is sort of interesting. And we can review some things we saw before. So the n equals 1 case, that's corresponding to K being a triangulation of the 1 sphere. 2 times 1 minus 1. Yeah, okay, so here's the boundary of an M-gon. We saw this result attributed to Coxeter at RZK. Just looked like a surface of genus G, where G was like 1 plus m minus 4, 2 to the m minus 3, I believe. So we're all good there. And then here something else is known. As far as I know, the only other case that's been settled. This was proved by Davis and Okun when, maybe 2001. Yeah, using a lot of like heavy duty, low dimensional topology. So using, yeah, I think so. Not an expert in this area, but sorry. Using L2 homology of like right angled Coxeter groups. And like deep results about the, I don't know, L2 invariance of three manifolds. I've asked a few people about the status of this conjecture. And during the focus program last summer, Ian Leary was here. I asked him about this case, and apparently this paper is known for being very hard. So he sort of suggested to me that a new proof of this case, or even just like some subcase of this case where you could bring some new ideas into it instead of taking their route where they really prove something much more general about group cohomology coefficients. Some new proof about, just any particular class of sphere triangulations, even in this subcase, would maybe be regarded as a rather big deal. So I think I wanted to just finish here, right? I'm phrasing this in terms of a real moment angle complex. The last 3 days, we've seen like a lot of different avenues or ways of thinking of a space like this, an intersection of quadrics, a complement of coordinate subspace arrangements, a polyhedral product for which we have a stable splitting, a Hochster formula way of thinking of the Betti numbers, and therefore this alternating sum of Betti numbers, right? All kinds of ways of writing down exactly what this Euler characteristic is. So are any of these connections with polyhedral products useful for this sort of problem? And I started on Monday trying to express some gratitude to Fred, and Fred, I think, would call this a homework problem. So homework problem a la Fred. He gave, whenever he gave math talks, he liked to give lots of homework problems. The 2020 thematic program, when he was here, he gave several, and I don't think anyone has solved them yet. So good luck with that one, and thank you for your attention.